Now, two very important continuous basis sets that you are going to use your whole life, or you have already been using, are the position and the momentum representations. So we're going to see those. And so hopefully this is going to clarify the issue a lot of you were struggling with, which was related to the question, why are cats in state space more general than wave functions? So we're going to start, and we have then, we're going to talk about position and momentum representations. Position first and momentum. And the assumptions that we're going to make here is that we have basis vectors. In this case, these cats are. And they are characterized by x, y, and z coordinates of a point in space. Now, this is pretty much, if you look back at our definition of continuous basis, which we discussed in the previous clip, you see that that is pretty much what we required. We wanted to have some linearly independent spanning set, which depended on continuous parameters, right? Remember that we had this omega nu or omega alpha. And here, if you consider the coordinates x, y, z, you see that they are changing continuously because they are giving you the coordinate of a point in space. And you can apply the same definition for basis vectors in the momentum space, these basis vectors P, which are characterized by Px, Py, and Pz, meaning their coordinates in momentum space, which also vary continuously. So let's have a look at the implications. What I'm going to do now is all those abstract things I was talking about, like closure relations, autonormality relation, etc., I'm going to apply to the specific basis, and then I'm going to argue the point, which I know some of you were insecure about. And this is a very important point, why cats and why state vectors are something more general than wave functions. Okay, so let's go for it. So we're going to have a look at properties. And we'll start with the easiest part, which is the R representation is the most common one. So we had said from the beginning that if you have a continuous basis, and we assume that these basis vectors are ortho, I always struggle with this, orthonormality. If they are orthonormal, this means that something like this has to hold, right? So they're continuous, they are orthonormal. Definition. So this property whereby I say that the inner product of R bra with R cat dash is delta R minus R dash, whereby this is the Dirac delta function, this has to hold. And if you look back, this was this property here. Can you see? So coming back to this issue, we can also say that if we want to define a closure relation, we are going to write integral d3r r is the identity operator. So it's pretty much the same issue that we had before, with the sum being replaced by an integral, now integral over all space. And we're going to use this to compute operators in this basis, to represent our states vectors in this basis, etc., etc., etc. And now, similarly, so these properties were related, we said these are concerning R, the R basis. Similarly, we have that for the P basis, we can also write inner product of P with P dash is delta P minus P dash, which is the condition that they are orthonormal. And we can also say that D3P P is the identity operator. So this is closure relation. Fair enough. So far, so good. Now, what we are going to do is we're going to see how we can write. So our task is going to be to write an arbitrary ket psi in position and in momentum representations. And hopefully this will make it clearer to you why wave functions are less general than kets. So let's do the following. We have seen how we do this for discrete basis. What do we have to do for a continuous basis? We have to write the ket, and we have to consider the closure relation, right? So we're going to start from this ket, which is equal to closure relation psi. So this is an arbitrary ket psi. So far, so good. So if you want to do this in position representation, you write then D3R psi. Correct? Yes. And so this is position. And if you want to write this in momentum representation, you have again, but now you use this. So this is in momentum representation. In this position. So this is nice because what you can see now is that you have some expressions which you may find strange, you don't know what to do, but we have defined a basis for our state vectors. So we expressed our state vector psi in two very specific bases, right? Now we know, and that's where I'm going to show to you that psi has to be 1, right? So the state vectors should be normalized. So they are, by their very definition, they are representing probability. So you know that this has to happen. So what am I going to do? Let's get this guy, right? We know that psi can be written as G3 R psi, and we're going to come with bra psi, this guy, from the left. Okay, so this is going to give me something like that. Now, does this look familiar to you? Well, let's look at something we know from our previous courses. We know that wave functions also have to be normalized, right, in R. So we know that this has to hold. Do you agree? Now, if you compare or if you use the closure relations, we can see that, so I'll compare this expression. What do you see? You see that this guy, so this is 1. Let me write it down that you know. So this guy is equivalent to this, has to be this, and this is this, right? So comparing, we then see that psi r is r psi, and if you take the complex conjugate as it should be, this is going to be all consistent. Remember how we defined our inner product? Remember that if you are dealing with an inner product in the state space, this has to be then just look, it has to be the complex conjugate of the inner product when you reverse the second and the first argument. If you are insecure, just look at our previous notes, but this is something that we have used in the axioms, okay? So write it down from previous lectures. Now, what we can also do is to compare this entity, which is this guy. No, I didn't want to erase it, sorry. This guy to the expression that we have. So we have something like this. We also wrote that psi is integral d3r r psi, right? So what you can see is that in this vector, you have this spanning set R, and you have these things which are like the components we have defined. So we can conclude that psi R is in fact R psi, which are the components of psi in the R representation. And this is quite important because you really see that this cat is more general. It's like you write a vector and you choose your vector, say you choose to write your vector in Cartesian coordinates or spherical coordinates or whatever coordinates. These entries that you're going to have, they are not the vector. They are the entries of the vector in a particular coordinate system that you are using to solve your problem because it's convenient. So you're representing your vector in a specific coordinate system. And you can do the same thing. I'm not going to do it, but you can try. You can apply the same line of thought to the P representation, meaning you can consider psi equal 1. You can write this as d3p psi p p psi, and you can identify these with psi star p and these with psi p. I'm going really fast with this because it's pretty much the same line of thought. And this is something that is important because for that reason, psi is more general than psi r, psi p. Invent any continuous basis you want, okay, etc. So it's more general than wave functions. Wave functions are like the coordinates of your vector in the state space. And if you define operators, we can also show. So let's talk about operators in this basis. You can also show using the expression we had for a continuous basis. Let's say get an arbitrary operator A. I'm going to write this in the position and in the momentum representation. So this is our task. Okay, so we have A, identity operator, A, identity operator. Now, position, right? Let's do position. So I'm going to have D3R, R, R, A, and here I'm going to have D3R dash, R dash, R dash, which is going to give me D3R, let me put it like this, it's nicer, D3R dash, R, A, R dash, R, R dash. So this is your matrix element, this guy is your matrix element of A in the position representation. And this is something which is quite useful when you need to compute these type of things. And you can also say in the momentum representation that A is going to be D3P, make it nicer, hang on, like this is nicer, D3P dash P A P dash P P dash. No, it's supposed to be a bra. Okay. Also, this means let's make an example. Let's have a look at how specific operators behave in this position space. So example, let us consider the X operator. I'm putting a hat here because I want to distinguish from the coordinate X. So I want to know how I can write this in the R representation, in R representation. Okay, so let's do that. I'm going to use then this formula here. So I have that X is going to be putting identity operators from left and the right, integral G3R dash R X R dash, and then here we have R dash. Okay, so I can do two things now. I can apply R to the right on this guy, or I can apply X on the left to this guy. So I can choose, doesn't matter, because what I'm going to end up in the end is, let me apply here. Okay, so here, let me just specify, I can apply this to the right or to the left. My choice. Do what you find nicer. It doesn't matter, I'm gonna get the same result. Because what you have from here, say I'll apply this to the right, okay? So if I apply to the right, I get X dash R dash. Remember that what I used here was this eigenvalue equation, whereby I say that X operator applied to R dash is going to give me X dash R dash, right? Note now that this is Kronecker delta of R minus R dash, which means that X can be written as, because you have this Kronecker delta, you're going to kill this one of the integrals, but I'm going to do it slowly. G3R, G3R dash. Then you're going to get X dash delta R minus R dash. Here you have cat R bra R dash, correct? Is the way it was set up, yes. So this means that R is going to be equal to R dash because of this, right? So that in the end I get D3R X R R, which is how you express the position operator, or the specifically related to this coordinate X in the R representation. Okay, so you can try the same, and it's something you might have done in your life. Okay, so if you are interested in trying and playing around with this, you can try, for instance, px in the p representation, or in the x representation, in the r representation, not x. We're doing 3D here, right? In the r. Okay, now we can also show, when this is important, because we need to know how we go from one basis to the other. And something we have seen in life a lot is a representation of P in terms of plane waves and things like that, right? So please note that we can also write that RP, which means the cat P in the position representation, is given by this. I think you all have seen this, right? When you say, you know, eigenstates of momentum are plane waves, etc., etc. You probably heard this in your undergraduate course. Be careful, because this is this P in the position representation. So if you look, this is a specific way of writing your cat's P. And how do you prove that? I mean, one straightforward way of doing this, let's use the fact that R and R dash are orthonormal, which means that you can write this delta function like this. But we also know that a delta function is also given by this expression. Make it, I would like to have a bit more space here. R minus R dash. And this divided by H bar. Correct? This is, if you are unfamiliar with properties of delta functions and you're struggling with that, have a look. Have a look at properties of Dirac delta functions is, if you are not familiar with that, is something that you find quite easily in the literature. If not, let me know or post a question. All right. So pretty much that's what we have. And we can do the following. We can do a comparison, right? Because we know also that the R, we can put a closure. Let me put a closure relation here. Okay. We are going to insert D3P P identity operator. So this is, for instance, a good example of how powerful these closure relations are. Because what we're doing now is like we're trying to move from one basis to the other, or we're trying to see what P means in the R representation, right? So we can insert this here. Can you see? It's something really useful. So if we do that, we find that D3R RP P R dash is equal to 1 to pi h bar to the power 3 D3P E I P scalar R minus R dash divided by h bar, right? Now maybe you see where I'm getting at, because if you compare, so I forgot the dash. If you compare, you see that you can write this as 1 to p 2 pi h bar 3/2. So let me do the integral before I think it's nicer to see. D3P E I P scalar R divided by h bar multiplied by 2 pi h bar 3/2 E minus I P scalar R tilde divided dash divided by h bar. Okay. So I wrote it in a way that is easier for you to identify. Like you can clearly see that this guy corresponds to this, and this guy corresponds to this here. So thus, we can say RP is 1 to pi h bar 3/2 EI P dot R h bar, and P in a product with R dash is equal to 2 pi h bar 3/2 E minus I P R dash h bar. Okay, so this brings the topic of basis change, because that is something that is happening. How do we do basis change? And this is quite useful, especially using these closure relations. And I mentioned a lot when I introduced them for the first time that they're quite nice for basis changes. And what we're going to do now is we're going to see some example. Okay, so now we want to change from R to P. So what do I do? Let me get the cat in the R representation. So this is going to be my start point, right? So we have seen that psi r, which is the wave function, is equal to inner product of r psi. So if you are getting confused, this is psi in r representation. This guy here, right? So we are going to use a closure relation in P. So we are going to write this as R psi using the identity operator. But we know that here we can also use D3P cat P bra P equal to 1. So we're going to do that. Equal to the identity operator, not 1, sorry. Fine. So we have then that psi R is equal to integral D3P RP P psi. Does this look familiar to you? I think a lot of you have seen these, right? Because what you have is that here we're going to have D3P 1 over, so let me write it already nicely. So this here is this guy, correct? So what I'm going to do is I'm going then to put here one over 2 pi h bar 3 halves E I P scalar R divided by h bar. And this here this is psi P. So this is psi in the P representation. And similarly, if you want to move from P to R, we're gonna go backwards, right? So from the P representation to the R representation, what you're going to have then, you have to consider, you start psi P, which is the cat psi in the P representation. So you can clearly see again that your wave function in momentum space is less general than your cat. And what you find is then you find that psi P using closure relation in R is D3R PR R psi. So this we know, this is psi R. And this guy here we also know is 1 over 2 pi h bar 3 halves E minus I P scalar R divided by h bar, which means that psi P is 1 2 p h bar 3 halves D3R E minus I P scalar R divided by h bar psi R. Okay, so one thing that you see if you look at this expression and this expression here is that 1 is the Fourier transform of the other. And this is quite a nice result, which you're supposed to know from your undergraduate course, but you can see how it comes really beautifully and naturally from using closure relations. And another observation, just to close this, we're going to see this in more detail in our synchronous lecture and some of the exercise sheets. But this is a very important statement because you are all used to some specific formulations of the momentum operator, right? So what I want to say is please note, and this is important, really, really important. Our operators, so the operators R and P, they behave differently according to the base. So the point that I'm going to argue is that, okay, you're all used to saying that P is something like that, H bar over I G R. This is really, really, really specific. This is very specific to when you are working in the R representation. And we're going to state here how they look. For instance, I'm not going to prove it, but it is nice if you can do it. But for instance, if you compute this, I want to write R, the operator R, in the R representation. So I'm going to have R, bra, operator R, and psi. What I do is I can apply, because I know I can use eigenvalue equations, and I can apply this here to the left, and I'll get then R psi, which then is psi R. And I also know now, if I do the same for P psi, I'm going to get, by applying this operator here on this bra to the left, I'm going to get P psi, which is psi P. And if you now decide to look at something else, you say, okay, I want to write R P psi, I can again apply this here, and I know that I'm going to get this. Can be done into detail. I'm not going to do it, but it's going to be in some exercise sheets because I think it's important. You're going to find something like that. Where I'm pretty much saying that this is minus H bar over I nabla psi R. And similarly, I can also show, if I have something like that, I can write this minus H bar over I whereby these operators, they are defined such as these nablas here. I think you guys call del, but everywhere in the world except in this country and US is nabla, maybe Australia, yeah, English-speaking places. So this operator you can write like this. So you have then derivative with regards to components pi, ei, and here you have delta xi, ei. So that is pretty much it with regard to continuous basis and the two important examples that we have just covered. And our next lecture is going to be about measurement, which is the third postulate.